Hello everyone, I'm Wei. I will host the tutorial today. The content of today's tutorial is covers two topics. The first, I will talk about learning bilingual word embeddings with lexical inductions, which is briefed in lecture 5, but I will give more details in this session. The second, I will brief the questions in regular exercise for this week. Okay. Like monolingual word embeddings, bilingual embeddings are also very useful in many NLP tasks. There are many languages in the world, but many of them have very little data resources. To make NLP systems that are able to serve massive languages, we would hope that NLP systems trained on a high-resource language like English are able to transfer its success to low-resource languages. In this context, we need strong bilingual embeddings. To do so, usually we need a large scale of training data with bilingual signals, such as bilingual dictionary and data parallel data. But Mikhail Artest proposed a different method, which requires almost none of such bilingual signals. Just a quick thought for this method. Such signals could be freely obtained from identical words, such as punctuations and numbers shared in different languages. Let's formalize the problem of learning bilingual embeddings. Suppose we have two language spaces, X and Z, and a bilingual dictionary with aligned word pairs. We let a rotation matrix W to align both spaces into a shared vector space with a goal that the embeddings of bilingual words with similar meanings are represented closely in a shared vector space. Now we'll have a look how it works in a high level. We start with the monolingual embeddings that are trained independently in different languages. And we also need a small size of bilingual dictionary with identical words, for example, which we call seed lexicon. Then we learn a rotation matrix through mappings to produce a large size of dictionary with high quality word pairs. Then we iterate this process many times to produce even much larger and much better dictionary in the end. We refer this machine learning techniques to self-learning paradigm. In the experiments, they also showed that the proposed method trained on even 25 English and Italian word pairs or trained on identical words can achieve the results as good as the method trained on 5,000 word pairs. This is quite exciting results, which trigger us to ask why this approach works so well. The first impression for the difficulty of this task is the initial dictionary is quite small, but it is clean. Later on, the induced dictionary is large, but might have misaligned word pairs produced. After the model being trained for many iterations, such type of errors could be accumulated to a very large extent, leading to the final dictionary with a very bad quality of word alignment. The secret weapons to address this issue from the authors is they resort to a very different training strategies, which are indeed independent from seed dictionary. They maximize the similarity between English words and their most similar neighbors in German. I will show you this makes sense if two languages share similar typology structure in the embedding space, which we call isomorphism property of languages. Let's see an examples. We adopt these training strategies to learn bilingual embeddings. After training a few iterations, as you can see, the embedding spaces could be amazingly aligned very well, even via a very simple rotation-based approach. Uh, Now you may have noticed that the seed dictionary never comes into play in this method. Here's the things. Both figures show that the models without involving seed dictionary doesn't work at all. As you can see in the right side, the accuracy in red and goes almost zeros. But when the word pairs comes into play, even with only a very small size of pairs, like 25 word pairs, the performance gets largely improved. And the reason is that training the training get sucked at a local optima after the model being trained for 10 iterations. Yeah, and we also, besides these observations, we also noticed that the model trained on 50 word pairs perform comparably to the same model trained on 5,000 pairs. Okay, so this is a very novel approach to show how to learn word embedding, how to learn bilingual word embeddings in a semi-supervised and self-supervised ways. Okay, that's all for the bilingual word embeddings in these sessions. Now we move to the regular exercise now. Let's have a quick review for the questions in this exercise. As usual, we provide bingo questions where you need to find correct statements from your understanding about multi-sense word embeddings, bilingual embeddings, and syntactic embeddings. You are freely refer to the slides from the lecture and exchange with your peer students. We also have the second questions for you on contextualized embeddings based on BERT. It is already known that BERT have been trained on the concatenation of hundreds of Wikipedia data. But does this training strategies produce some unexpected outcomes? What problems in the resulting embeddings do you observe? Please explain this up to 5 sentences. And in the last questions we provided, namely, it is a common issue that certain words and tokens are missing from the embedding vocabulary, so-called out-of-vocabulary issues. Please list at least 3 possible solutions and describe it. Okay, that's all for the exercise this week. Let's review the solutions in this exercise. The first bingo question is which of the following statements about sense disambiguated word embeddings are correct? The second statement is wrong because it's talking on written words with the same meanings but multi-sense word embeddings. The definition of the multi-sense word embeddings is about 2 similarly written words with different meanings. So they are apparently talking on different things. The second question is about bilingual embeddings. The first statement is correct because many languages share similar syntax and vocabulary. Training a model on multiple languages indeed could leverage the shared structure of input spaces, so they can handle low-resource languages. For the second statement, which is not correct because Indeed, this is being discussed in the tutorial. Bilingual embeddings could be learned by identical words such as numbers and punctuations in different languages. And for the last statement, BIVCD, in BIVCD relies on a monolingual model, which is trained on the comparable documents of different languages. Okay, the last question is about syntactic embeddings. The context in word vector do not include information about the word order, which is correct because it doesn't encode the positional information during the training. For the second statement, scriptogram models is indeed based on word context of a fixed length, not variable length. The last statement is about dependency-based embeddings, which is correct because it can learn the relations between words, even two words being very far from each other. So this property of the embeddings are able to solve the problem of the long dependencies. Let's move to the second question, which is about contextualized embeddings. Multilingual BERT is trained by running standard BERT on the concatenation of hundreds of monolingual tests in Wikipedia. Does this yield monolingual contextualized embeddings? What problems do you observe? Monolingual BERT embeddings for mutual word translations are indeed misaligned in a shared vector space because during the training, the cross-lingual signals, such as parallel data and cross-lingual dictionary, are not involved. Besides, languages always have very different linguistic features, which makes them not equally hard for learning static and contextualized embeddings. For example, German has higher inflectional morphology than Chinese. This brings the performance gap between languages in the zero-shot cross-lingual transfer setup. For example, we usually train the system in English and test its performance in different languages. Okay, let's look at the last question, handling out-of-vocabulary words. When using pre-trained word embeddings, we always can observe that some tokens are missing from embedding vocabulary, which we call out-of-vocabulary issues. Think of at least 3 possible solutions. First is we do nothing. We just ignored out-of-vocabulary issues. This will definitely lose a lot of information and the performance is very bad. The first solution is introduce an unknown tokens, but this cannot distinguish different out-of-vocabulary words. Next solution is about using one random vector for every out-of-vocabulary word. Right, but the quality of these random vectors could be very different. Next is using character or subword embeddings. This probably is the best solution because the current state-of-the-art BERT-based embeddings is using this solution during the training. Next is looking up the token from the internet and the average embedding and average vectors. This might work because we can find some synonyms. We can find some synonyms from the internet, and some of them can be found in the embedding vocabulary. Then we average them to obtain the final embeddings for the token missing from the vocabulary. Okay, I think that's all for this exercise.